Hey everyone, in this lecture today we're going to be talking about oceans. And we're fortunate enough here in Southern California to have the Pacific Ocean nearby. So some of the examples that I'll be using today, we can actually see ourselves from the beach. So some of the learning objectives of this lecture is why ocean basins exist and how we explain different variations in water depth. We call that bathymetry. We're going to talk about the nature and causes of surface and deep currents, the behavior and cause of tides, why waves form and how they behave, and how a great variety of different coastal landforms develop and evolve, and how rising sea level, wave erosion, and human activities affect coasts. So first, let's talk about bathymetry. So I've used this word before, and it might make sense if you think about it in terms of topography. So if you walk up a hill, you're increasing in elevation, and we call topography the changes on the surface, the changes of elevation on the surface. Now, if we were to try to describe what's happening below the water or below sea level, we call that bathymetry. This is the variation in depth of the seafloor. And we're able to measure bathymetry from satellite surveys, and we have more precise ways of measuring the seafloor. And we can look at very subtle differences in the seafloor to tell us more about how maybe where fish live or how different environments affect currents. And we look at bathymetry to determine where boat channels should be. All sorts of things come out of understanding better bathymetry. So here's a quick YouTube video about how bathymetry is used and what the bathymetry detail looks like in Australia.
Bathymetry is the study and mapping of seafloor topography. It involves obtaining measurements of the depth of the ocean and is equivalent to mapping topography on land. A bathymetric survey produces a map that charts the contours, depths, and hardness of the ocean floor. Bathymetry maps are available for some of the world's oceans and seas. However, in deep oceans, the maps are mostly very low resolution. In the search for MH370, a survey is being undertaken to provide detailed bathymetric information in the priority search area. This video shows data acquired by Geoscience Australia in a previous marine survey in deep water to the northeast of the current search area. It does not show actual data captured in the search for MH370. This data demonstrates the level of detail being gathered to support the search.
So now that we have an idea of how much detail can go into bathymetry, let's look at a map of the world here. And you're going to have to tune your eye a little bit to this, because what's in the no color or black are the continents. And so what you're looking at is a colored map of the oceans. And here, the different colors represent the different bathymetry, the different levels of the seafloor. And so the bluer colors mean it's deeper, and lighter colors, green and yellow, mean that it's shallower. So of course, right along the coastlines, we usually see some, more shallowing bathymetry, shallow here. But if you've ever been in the Pacific Ocean off the coast of California, you know that it is very cold and it can get deep very quickly. And so we see that reflected here with our bathymetry map. And of course, everything about this course is always related to plate tectonics. So do you see a correlation between plate tectonics and bathymetry? Well, some of the places that might be interesting, actually, I'm going to close this, is over here between North America and down here is the tip of Africa. It's a little bit challenging to see, but here you can actually see that this is quite shallow. In the Atlantic Ocean is quite shallow. So this tells us something about the plate boundary that exists here. So there is a correlation, of course, between bathymetry and plate tectonics, and it's more apparent in some of these different areas of the world than others. So let's talk about some of the vocabulary. We have continental shelf, and this is a relatively shallow portion of the ocean that fringes the continent. We have the continental slope, and that's a gentle change of slope of the continental shelf that gently decreases in depth. We have an abyssal plain, and that's a nearly horizontal surface. And we have a submarine canyon, and that's relatively narrow and deep valleys that downcut into continental shelves and slopes. So you might be familiar with the continental shelf. Like I just said, if you go visit the beach, you might notice that off the coast of Southern California, it gets very deep very quickly. If you've ever taken a boat to the Channel Islands, for example, you know that the water can get quite deep. It's very dark, it's very cold. Versus on the Atlantic side, we have a much shallower continental shelf and slope, I should say. So the slope is more gentle in the Atlantic side than it is on the Pacific side of the United States. Okay, so ocean water and its movement. We're going to talk about these different things here. First is the composition and temperature, then currents and tides and wave action. So let's look at it in more detail. So have you ever noticed that you float more easily in ocean water than in fresh water? Why do you think that is? If you've ever swam in the ocean, you might realize that you are more buoyant than if you're in a swimming pool. Well, ocean water contains an average of 3.5% dissolved salt. It means it's saline. So salt in the water increases the water's density, and therefore you're more buoyant. The concentration of salts in the water is called salinity. And salinity reflects the balance between the addition of fresh water by rivers or rain and the removal of water through evaporation. So when seawater evaporates, the salt stays behind. Salinity is also dependent on water temperature. So warmer water can hold more salt in solution than cold water. So I'm going to hit pause on this in a second. What I want you to do is also hit pause on the video and look up some of these different salinities based on the body of water. So if we look up the salinity of the Pacific Ocean, how does that compare to the salinity of a sea or the Salt Lake? So if you've ever been to Mono Lakes on your way up to Mammoth, you might have noticed that there are these really interesting salt formations. And it's a really cool place to visit if you haven't been there before. So what I want you to do is look up these salinity values and write them down, and we'll talk about them in a second. So hit pause now.
A little later.
Okay, so I've completed this chart as well. And does it surprise you that some of these salinities are so different from the other? Do you think there's a correlation between type of body of water and its salinity? And why do you think that is? So we see that the Pacific and Atlantic Ocean, the two oceans I have listed here, are about the same salinity, 33 to 37 parts per thousand. And then we look at some of these seas, like the Salton Sea, which is 44. I would have probably expected the Salton Sea to have a little bit more salinity than the ocean, but it makes sense. And then, like I said, if you've been to Mono Lake, you see all those salt formations that have been left over from evaporation. So of course it has a lot of salinity. And there's one, the saltiest body of water on Earth is called Don Juan Pond. And that has a salinity of 338 parts per thousand. That's very, very salty. So like I said, the composition is also dependent on temperature. So we just talked about salinity, but what about temperature? The average temperatures correlate with latitude because the intensity of solar radiation varies with latitude. So if you've been to the Caribbean, then you know that the water is a bit warmer there. So temperature is different because it's closer to the equator. Water temperatures in the ocean also vary by depth. If you've swam in a pool, you know that the shallow section feels warmer than in the deep section of the water. That's because water is warmed by the sun and expands, therefore becomes less dense. So it tends to float near the surface or sea's surface. And a thermocline is the boundary below which water temperatures decrease sharply. This is about 300 meters depth in tropic regions, and polar regions don't really have a pronounced thermocline because there isn't as much variability in temperature as we do see it in tropic regions. Let's talk about currents now. So these are basically the rivers of the sea. This is where ocean water moves in a continuous flow at velocities up to several miles per hour. Currents are not defined by channels, or they're not confined by channels like rivers are on land, but they are defined by changes of velocity. Currents can cause water to circulate around the oceans and between oceans at different levels. So we have surface currents and we have deep currents. And maybe you've observed currents before visiting the ocean, or uh, noticing different water temperature. Sometimes you would be in wading in the ocean, and you feel a slight change in temperature that might have to do with a surface current, and this can affect up the first few 100 meters of water or so. And then we also have deep currents, and this affect the remainder of the water column in motion. And so surface currents and deep currents affect different parts of the ocean, of course. Surface currents deal, if you're into boating or sailing, that might impact, surface currents might impact your path or how you get from place to place. And deep currents can affect movement of sediment or wildlife deep in the ocean. So another type of current is the Coriolis effect. This is a phenomenon that causes surface currents in the northern hemisphere to veer toward the right, and surface currents in the southern hemisphere to veer towards the left. And the Coriolis effect explains how hurricanes are formed. So if you think about how wind moves in a direction, say the wind is trying to go from south to north, for example, and we can represent that as a vector. The Earth is spinning, and so the vector then spins with it, and that's in essence the Coriolis effect. So we also have a gyre, which is the across the width of an ocean, the adjusted motion can lead to currents making complete loops, and we see these types of things with massive storm systems like hurricanes. So here's some vocabulary. We have a downwelling zone, and this is where surface water sinks. And we have an upwelling zone, and this is where deeper water rises. So what do you think some of the reasons are that you would have these different zones of upwelling and downwelling? Well, I already explained one of those situations where you might feel a little bit change of temperature, and that could be due to currents or changes of salinity. We also have wind that can blow surface water shoreward. Another example is when we have oversupply of water that develops along the coast or surface of water, and that must sink in order to make room. So this is where we have a large storm event or something where you have a big rainfall and an influx of fresh water into the ocean, for example. We can also have wind that blows surface water away from the shore, creating a deficit near the coast, and therefore deeper water must rise to fill that gap. And of course, we just talked a little bit about the Coriolis effect near the equator. So here's a map of the world, and this is generally speaking where currents exist and the direction in which they exist. So here, if we look over on the Pacific side, this is why some of our coastlines are so cold, is because we have this cooler water out in the middle of the Pacific that comes along our coastline and south. So there really is no place to get warm water out here. Versus in the Gulf, we have water that comes from the equator up. And so if you're on the Atlantic side, this is why the water in the Atlantic side is generally warmer, is because we have a general current that moves water from the equator, which is much warmer, up into towards the Atlantic side, and this is called the Gulf Stream. So here we can see these different currents and generally where they flow. I've had a chance to visit part of Norway, and I was surprised to be so far north, but the water was not very cold and the temperatures were tolerable. And that's because we have this Norwegian current. It's a warm current. And so even though you might be really, really far north and you think, geez, that's very cold compared to, other parts of the world like Russia and Greenland and northern Canada, it's quite warm because we have this current that pushes everything from the North Equator and the Gulf Stream all the way up into that part of the world. Okay, so now let's talk about tides. Tides are the rise and fall of sea level. So twice daily, we have a tide. If you're into surfing, then you probably check the tide report. Or if you like to go swimming, you might check the tide as well, because you want to be in the water at the time that benefits you most. So you might check the tide report. And the tide is in response to a tide generated force. And it basically, in a nutshell, has to do with the gravitational attraction of the sun and moon. And this creates a centrifugal force produced as the Earth-Moon system revolves around its center of mass. And so it's basically because we have the moon is why we have tides. And the tidal reach, that's the elevation difference between sea level at high tide and low tide. And that can be quite different depending where you are in the world. So here's a little diagram of this that explains why we have tides. So we have this gravitational force. The Earth has a gravitational force, so does the moon and the sun. And it basically pulls, the gravitational field pulls ever so slightly in one direction, depending on where the moon is relative to the sun. So if the moon exists between us and the sun here in this way, we get a slight elongation in this direction. And then as the Earth rotates and the moon is in a slightly different orientation, we get elongation in the other direction. And this is why we have tides. It creates these little bulges. And these bulges occur on the different sides of our planet. And this is why we have tides that happen twice a day. So here's some images of high tide versus low tide. This is low tide here on the left, and we can see that there's some, here this is like the shallow beach area, and we can see that there's a little cement structure here. And then at high tide, this is completely filled in. So that looks like quite a bit of difference between low tide and high tide, probably a few feet or so. Here's another example where this whole rock side is totally exposed at low tide, and then at high tide, it's completely filled in. All right, now let's talk about wave action. An ocean wave is a periodic undulation of the surface water. Okay, so the low part of the wave is called a trough, here in this diagram on the right. The high part of the wave is called the crest. The distance between these two, the distance between crest and crest is called a wave length. That would be from point A to point B. That's called a wavelength. And the elevation difference between the trough and crest, so the elevation between the lowest point and the highest point, is called the wave height. We also have wave frequency, which is the number of wave crests passing A at each point. So how often does a wave pass this point? And the wave period is the time required for the wave crest at point A to reach point B. So ocean waves develop because of shear motion between air molecules and the wind and water at the surface of the sea. And the character of waves in the open ocean depend on the wind's strength, which is how fast the air moves, and the fetch, which is the distance over which it blows. So with continued blowing over a long fetch, we have swells. And so if you are a sailor or if you've taken a boat, you might experience some really large swells, and that has to do with the winds, in essence. So constructive interference of waves is the interaction of waves and currents, and the focusing of wave energy due to the shape of the seafloor can lead to growth of rogue waves. So maybe you've experienced some constructive interference of waves, and it feels like a really big crash because you're used to maybe if you're standing in water, you would feel the waves coming in and out. And suddenly, if you get hit with a rogue wave, it feels very disruptive because it's different than the normal wave action. So waves may make a large angle with the shore as they come in, but they bend as they approach So they reach the shore in crests that make about 5-degree angles with the shore. And wave refraction occurs when waves approach the shore at an angle. And if the wave reaches the beach at an angle, it causes a longshore current and a beach drift of sand. So this YouTube video here is going to demonstrate that a little bit further with some diagrams. So this is a good one to watch. And again, if you're a surfer, then you're probably really familiar with longshore current, and you'd want to understand these to catch the best waves.
This module on wave refraction will help you with this part of the assignment. As waves come into water shallower than the wave base, which is defined as a depth of half the wavelength, the orbital movement of the waves begins to feel friction with the bottom, and the waves begin to slow down. The shallower the water gets, the slower the waves go. As they get into shallower water, they bunch up together, grow taller, and eventually break. But the other thing that the waves do before they even break is what's called refraction, which is the waves bending and changing direction as they slow down in shallow water. Here's an animation that shows wave crests coming in straight to the beach. And what I want you to imagine here is that off of the headland where the lighthouse is, the water here is probably shallow, whereas it's deeper over here in these two bays on both sides. So the waves slow down more here and less here, and that causes refraction. You can see how the waves are bending and changing direction. Now the reason this is important is that if we put arrows on the waves showing how their energy gets directed, the refraction causes the energy of the waves to be concentrated in the shallow water near the headlands where the waves wrap in and push together. So you're going to see the biggest waves and the most erosion right here, whereas the energy of the waves gets spread out in the deep bays on both sides. So the energy here is dissipated, and here you're going to see kind of small waves. Now this process of refraction of waves bending in over shallow areas is very important for forming big surf waves. And we're going to look as a case study at the Mavericks wave in Northern California near Half Moon Bay. Pretty good picture of me here on the Mavericks wave. Yeah, right. Mavericks is a really marvelous wave. It only gets going a few times a year, but when it's on, it's ferocious, and it's a world famous wave. This picture shows what's sometimes thought to be the world's greatest wipeout. Jay Moriarty wipes out at the top of the wave and falls more or less 60 vertical feet through the air at the bottom of the Mavericks wave. Mavericks is located south of San Francisco, right here, off a point of land near Half Moon Bay in Central California. What I want you to do now is go look at the video called The Science of Big Waves that is going to explain for you, among other things, why there's a big wave that forms here at Mavericks. The key is refraction.
So like the video explained, here are some of those definitions again. When we have a longshore current, this is where the wave arrives at the shore obliquely, and the water is nearshore region has a component of motion that aligns with roughly parallel to the shore. When we have a longshore drift, this is where the waves roll into the shore at an angle. And then sediment in the surf follows a sawtooth pattern of movement that results in a gradual net transport of beach sediment parallel to the shore. This sawtooth pattern happens because an oblique wave carries sediment diagonally into the shore. And then we also have a rip current. This is where we have excess water that moves back to the sea in a localized strong seaward flow that's perpendicular to the shore. So maybe you've experienced some of these things here in Southern California. The longshore current and longshore drift is a reason why the area Mondos is really popular for surfing, is because we have those waves that arrive obliquely to the water. And you might have also experienced rip currents, because they're also very common here. So here's an example of a rip current. This is from Zuma Beach. So if you've ever swam in a rip current, swum in a rip current, then you know that it's really scary, because basically what happens is you have water that comes in and then basically turns around and forces water back out in a perpendicular to the shore. So where you see this little sediment churning here, this is an aerial view of a rip current. And this is from Zuma Beach, which is a little bit further down the coast, kind of near Malibu. So if you ever experience some rip current action, maybe you want to figure out how to best practice safe swimming, you can check out this link from the lifeguards about how to swim in rip currents. And in a nutshell, I'm going to tell you right now, but I recommend you check out this website, is that you want to swim in the perpendicular to the motion. So if you're experiencing a rip current, the rip current is going to force you out this way. You'd want to swim in a perpendicular motion to that. So you'd want to swim parallel to the sea line here, to the coastline, and therefore perpendicular to the rip current. So let's talk some more about coastal landforms. We've covered some of this already in depositional environments, but I love depositional environments. They're super important. So let's talk more about it. First up, beaches. So here's a diagram of some beach. Here we have some of the things that we've just talked about, these different wave action and wave movement approaching a beach. Typically, we swim in the surf area, but if you are a surfer, then you'd want to understand where some of these wave movements are coming from. And we have a lot of different sediment that's being churned up through here. And sediment can be deposited, and this is where we get our beach environment. If you go to the beaches here in Southern California, we usually sit here around the beach face or the berm. And then there's quite a few dunes and beach cliffs as well. And in one of my videos, I showed you a lagoon system near Mugu. And so right near Mugu, we would see a lagoon and a dune right next to each other. So here's some more vocabulary. A sand spit is where the coastline indents landward, and we have longshore drift can extend a beach out into open water, and some form across the opening of a bay to form a baymouth spit or a baymouth bar. We have things like barrier islands, which form in regions with an abundant sand supply, and bars may rise above the sea level. And then we have a lagoon, which is the example I just showed, which is where we have waves that lose energy as they wash onto a barrier island. So the water between a barrier island and the mainland becomes quiet. And so here's an example down here of some beach drift. And this is where we can generate some sand spits and baymouth bars. So here's a little spit. We can see that the beach kind of does this curly action here. And then we have some bars out here as well. So it has to do with the shape of the coastline and where sediment is being able to be deposited. In some of these examples here, we have more of like a muddy and wetland type of sediment being deposited. And of course, near the coastline, we have more of that sand because the wave action is able to deposit sand in a higher velocity system, and lower velocity systems like we see inland and in estuary is where we see more mud and things like that. Okay, so that describes a beachy type of coastline. What about a rocky coast? This is where we have a combined effect of wedging or abrasion and basically a wave erosion that cuts a notch into the coastline. So where we see beaches being formed, that's a sign of deposition, but we also see lots of erosion due to waves. And so as a wave approaches a coastline, it can create these notches and it basically cuts out a coastline. And here's an example of that, and a picture of that. And so, of course, this makes for not the most stable cliffside. And we see this being a problem with some coastline communities where they build on top of, not this one, but in some parts of like the Bay Area where they've built homes high up on a cliff, and the ocean keeps cutting it back and keeps eroding it away. And so some homes just fall right into the ocean. So when we have further undercutting, it can break away at a joint. So instead of just eroding away just a part of the coastline here, it can actually take away whole joints. And so, so a whole sheet, for example, could get broken off. And the cliff can retreat, which leaves behind wave-cut bench that becomes visible at low tide. So here's an example of some of those rubble that's left behind that we see exposed at low tide. So coasts are irregular with headlands protruding into the sea, and embayment can be set back from the sea. So these are just more vocabulary words when we talk about different types of coastlines. We have wave refraction that focuses wave energy on the headlands, which accelerates their erosion. So in some cases of headland, it erodes in stages. So these pictures might look, this might look familiar. I don't think this is a picture of Anacapa Island, but we see things quite like this along the Channel Islands, where we see cut-throughs, basically, of the rock. And this is where we get that distinct shape for some of our edges of the Channel Islands. I'm going to move my face so we can look at this diagram. So in the diagram over here, here's some more vocabulary words where we have, this would be an example of a sea arch. This is very iconic for Anacapa Island. Here are things like a sea stack. This is where we have embayment. So these are just some of the words where vocabulary where the coastline is eroding away, creating those wave-cut notches that we just talked about. So in some areas we have deposition, in some areas we have erosion. Okay, next up is a rocky coast, is a fjord. And this is where we have rising sea fill in a deep valley, typically filled by glacial water or glacial runoff. And coastal fjords are fingers of the sea surrounded by mountains. Fjords are very common in places like Norway that I just shared with you of why Norway felt so warm. Here's a picture of me in a fjord. This is basically me on the boat there. It's actually just stunningly beautiful. The water is very clear because it is typically fresh water. The glacial runoff, it's because it's fresh water. There's a lot of clarity and it's filled these deep fjords. So it's very strange to be in a body of water where the cliff sides are so tall next to it. Okay, so let's talk about organic coasts. Organic coasts live along or exist along where organisms control the landforms. So this would be an example of a wetland or a swamp. So coastal wetland is vegetated, flat-lying stretch of coast that floods at high tide, but generally does not feel the impact of strong waves. And this can include things like marshes, swamps, and bogs. So here's a picture of a wetland is dominated by grasses typically, where a swamp has a lot of trees. A bog has moss and shrubs. So these are some slight differences between the terminology of what makes something a wetland versus a swamp. And it has to do with some of these organisms that control the coastline. Okay, so let's talk about coral reefs. So a coral reef is a colony of tiny invertebrates, and corals obtain part of their livelihood by filtering nutrients out of seawater. If you've been to more areas that generally have warmer water is where we see more coral reefs. And they are quite beautiful to look at because they have so much different life. It builds life for fishes and all sorts of stuff. So reefs absorb the wave energy and therefore serve as a buffer zone for the coastline. So here's an example here of a coral reef that creates a lagoon, and the water that would be inside of this lagoon would be quite protected because the coral reef absorbs all of that wave energy. All right, so let's talk about some causes of coastal variability. We're going to go over these in a little bit more detail. So first is relative sea level changes. And we're going to talk more about sea level change in the climate change lecture in just a little bit. So as sea level changes, that means as water rises or falls relative to land surface, these can occur over geologic time. So we do see sea level changes within our lifetime, human life, but also we see quite a bit of fluctuation of sea level in geologic time. So some of these changes affect the oceans worldwide. And so a word that we use to describe that is called eustatic sea level change. And this reflects global variations in sea level spreading rates or sea level rise and fall. These changes may also reflect growth or shrinkage of ice glaciers, which store water on land and keep it out of the sea. So that's one thing we're experiencing right now is we're seeing a lot of melting of these glaciers, and therefore we're seeing an influx of sea level. So here's an example of the United States, and we have here's some glaciers in the Canadian area, further North America, and this represents the forest, and down here we have grassland. So we can see that what once was the coastline 18,000 years ago or so has now retreated quite a bit back to present day. So present day is this black line, and 18,000 years ago it was much further out. And this also explains, we use this information to figure out the bathymetry. So we have an idea of where that coastline was because we can understand the slope of the coastline, and so we use bathymetry to help figure out what sea level was like at one time. Okay, so we also have an emergent coast. This is when land is currently rising or rose in the past relative to sea level. And so over time, what we see here is that if the sea level changes drastically, this would change quite a bit of the land surface. So we have over time what once was a beach with wave cut action here, and we have a sea level over time if sea level falls and we have a rise of the land surface. What once was that exposed bench here from the wave cut bench is now totally on the landform. So we see some of these features present day, which help us understand the past of what sea level used to be like. Another example of this is a submergent coast, and this is where coasts where the land has been sinking relative to sea level. So landforms include things like estuaries and fjords. So like I just showed with a fjord, that's because we have a lot of glacial runoff and glacier fill. So all that water has come down from the mountains and filled this valley. So the valley was once a valley where you could walk on it with grass and things like that, but then it's now been filled with glacial runoff, so we have a relatively higher sea level. Okay, so when we talk about this, we talk about how it changes the sediment supply. So in some systems we have deposition, in some systems we have erosion. So in erosional coastline, this is where waves wash sediment away faster than it can be supplied. We have accretionary coastlines, and this is where there's more sediment arrives than is washed away. So we have erosional processes, and then we have depositional processes here. And the climate can also impact the rate in which erosion or deposition takes place. And this has to do with organisms' growth or presence. Like I said, coral reef is one of those that protects the coastline. So that would be one of those things that protects a coast from erosion. We can also have a change in wave energy. So like I said, if there's a heavy wave that comes in and it eats away at the coastline, that's where we get those notches. And temperature also seems to affect this because temperature can affect salinity. So if you're in an environment where the coastline can eat away at a rock, the warmer it is, the more saline it can be, and that has consequences as well. So let's look at some contemporary sea level changes. When water level changes often during, like I said, water level changes often during geologic time. And so we can see that change, but we also see it relatively within our contemporary lives. So if, and on a time scale of hundreds to thousands of years, we see relative sea level rises and falls. If sea level continues to rise and reach about 3 to 4 feet, coastline cities would be greatly impacted. So here's a diagram of the outside here, this is present coastline, the black line. But if we were to, this is from about 14,000 years ago. This is roughly that same line that I showed in that previous diagram. And if we have continued melting and we had sea level rise of about 3 to 4 feet, that would mean that large cities like New York and DC and Baltimore would be in trouble. They would probably be heavily impacted by sea level rise. And it's not unreasonable to think that sea level would rise that much because about 14,000 years ago, we can see where the coastline used to be. So some of the things that we do to try to prevent or further erosion of our beaches and protect what we have now is we have some man-made structures. And these are called, you might see these, and I have an example of that in just a second. So we have a groin, which is a concrete or stone wall that protrudes perpendicular to the shore to prevent longshore drift from removing sand. We have a jetty here, and this is a pair of walls to protect the entrance to a harbor. And what's most common here in Southern California for a lot of our harbors is a breakwater. This is an offshore wall parallel or maybe at an angle to the beach to prevent full force of waves from reaching a harbor. And so here's an example of that. Here is the Channel Islands harbor, and here's an example of the breakwater at the mouth. And so this prevents waves from entering the harbor or causing erosion right here near the harbor. Okay, so we just went through quite a bit of information here about the oceans. So first we talked about why ocean basins exist and how to explain variations in water depth, and that's called bathymetry. We talked about the nature and causes of surface and deep currents. We talked about tides and behavior of tides. We talked about why waves form and how they behave, and how a great variety of different coastal landsforms develop and evolve. We've also touched on this in previous lectures about depositional environments and systems. And we touched briefly on how sea level rises, how that affects erosion, and of course, how that impacts our coastlines. And we're going to talk more about sea level rise during the climate change lecture near the end of the semester. All right, that's it for this. Bye.